All right, let's take a look at the warm-up today. Find a general solution to the differential equation shown here. So far we only know how to solve higher order differential equations if they are linear, they are homogeneous, and they have constant coefficients. What do you know? We have all those things here, right? All right, so we can solve this thing. We're going to use our general process. Step one is to assume a solution. Assume that x equals e to the rt is a solution. We then take the derivatives of this, we plug it into our differential equation, we factor out that e to the rt factor that's in each of the terms. That leads us to part two here, which is generating our auxiliary equation. So in this case, we have an auxiliary equation of r squared plus 3r plus 3 equals 0. Any question about where that auxiliary equation comes from? All right, next thing we have to do is find the roots. So 3 says find the roots of the auxiliary equation. So I'm looking at that thing, I'm trying to factor it. Factors of 3, it breaks down to 3 times 1, and then a bunch of stuff with fractions. I really don't see anything, which means I have to do what? What do I need to use here? Quadratic formula. So we have r is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. In our case, we have b is equal to 3. So I have negative 3 plus or minus the square root of 9 minus 4 times 1 times 3, which is 12, all over 2 times 1, which is 2. So I get a negative 3 halves plus or minus the square root of negative 3 over 2. So what do I have here? Looks like I have complex values, negative 3 halves plus or minus I times root 3 over 2. So I have complex values. Now, does that look pretty ugly? Right? Doesn't look nice, but the answer is not always going to come in integer values. So you should be expected to be able to handle something like this. This isn't too crazy. You don't have to give me any kind of numerical value for root 3, but you have to put root 3 in there. Any questions about the roots? All right. Next, form. We are forming the solution. So form the solution based on the form of the roots. So in this case, we're in the complex case. That means our solution is going to look like e to the alpha t times the quantity c1 cosine of beta t plus c2 sine of beta t, where our roots are alpha plus or minus beta I. So in our case, our alpha is negative 3 halves, and our beta is root 3 over 2. So then we just plug in those values, e to the negative 3 halves t, c1 cosine of root 3 over 2 times t, c2 sine of root 3 over 2 times t. And that should be our solution. Any questions? We'll certainly see something like that on the quiz today. Any questions? All right. Plan of attack. Number 1. Apologize. Did I spell it? Maybe. Done with the exams. I'm almost there. Definitely by Thursday. Spent all weekend in Berga at a hockey tournament, grading the whole time in the little warm area. So I'm not quite there though. So I still gotta tabulate them basically and enter them. So Thursday, sure term. 2, we're going to do a general overview of sections 2.3 and 2.4. What we're going to do is we're going to take a step back and we're going to look at the theory of higher order linear differential equations that are just linear differential equations, not necessarily constant coefficients. We'll do a broad sweep of all the theory, and then see how it applies to kind of our specific case that we can solve. And then lastly, we'll have our quiz. All right, so big theory ideas. You're going to see a lot of repetition in these little mini slides here. We're going to start off with this one, a little correction right away. Get rid of that guy. This is a general nth order linear differential equation. We can always write them in this form here. Right? So we have a bunch of coefficients to a bunch of derivatives. First coefficient, the leading coefficient, is a sub n of t. Right? In this case, that really could be a function of t, not necessarily a constant. This equation up here is still linear. Right? So this is just an nth order linear differential equation. And we'll start by looking at our existence and uniqueness theorem. Okay? We kind of talk quickly through about 3 different statements of it. Now I just want to summarize it exactly what we need. When does there exist a unique solution to this thing? So we're going to say there exists a unique solution around some point, t sub naught, some initial t value, if a sub n of t sub naught is not equal to 0. That's the leading coefficient. So step number 1, right? Look at the leading coefficient. For what values of t is that thing 0? Those are values of t where there does not exist a unique solution. Okay? So the leading coefficient can't be 0. Next, a sub n of t, a sub 0 of t, blah, 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 everything in between here. All of those coefficients have to be continuous at t sub 0. Okay? And then lastly, f of t also has to be continuous at t sub 0. That sounds like a bunch of words, right? A bunch of continuous, smooth stuff there, blah, blah, blah. It basically says if any of those coefficients are 1 over t, guess what? T can't be equal to 0. Okay? That's really the gist here. If any of those coefficients are the natural log of t, well then t can't be negative numbers that we're going to put in there. Okay? All right. Any questions about the statement? All right. And then an example. Consider this differential equation. This is a second order linear differential equation. So that fits our general form here. For what values of t are we guaranteed there exists a unique solution? Yep. Yep. Good. Yep. Right? T can't equal 2. Certainly 1. So t can't equal 2. What else? Yep. T can't equal 0. Can't equal 0. Well, why not 0? I don't see 1 over t anywhere. That leading coefficient is t squared. That leading coefficient can't be equal to 0. Okay? So where does there exist a unique solution? For all t such that t is not equal to 0 and t is not equal to 2. Or how about for all t in the intervals from negative infinity to 0 or 0 to 2 or 2 to infinity. Those are all valid solution intervals. So once again, all the coefficients are continuous and the leading coefficient is not equal to 0. Any questions about existence and uniqueness? Yep. You did what? Union? Yes, I think so. The big idea is that we got to be careful that solutions can't cross over these things. So if you're looking for the set of all values that are good for t, then yes, it can be the union of all those sets, right? But as intervals, we got to make sure that we understand they can't cross over. Okay? All right. Other questions? All right. Next big idea, next big theory piece here. Once again, you don't have to recopy this whole thing. It's basically the same statement, except now it's homogeneous. Given an nth order linear homogeneous differential equation, as shown, here's our big example. We need n linearly independent solutions, x1, x2, x dot 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 xn, to form our general solution. And then this is how we form our general solution. We've talked about this before as well, right? We talked about this from a linear algebra standpoint, that our solutions to this homogeneous equation are basically a vector space. And so what we're finding is x1, x2, x3, we're basically finding a basis for this vector space. That's another way we can view it from linear algebra. Differential equation, we need n solutions. But not just any n solutions, they have to be linearly independent. And up until now, we've only looked at cases where we have two solutions. We said, how do we tell if these two solutions are linearly independent? Basically, they can't be multiples of each other. That's what we've looked at. However, in a more complicated case, where we have 3 solutions or 4 solutions, it becomes much harder to see if they're linearly independent or not. Because it's not just are they multiples of each other, is there any way I can take a linear combination of all the other pieces to get this piece? So really, we need a test to show this independence. As long as we know we have independent solutions, though, we can just write out our solution like that. So here's an example. Same differential equation, except the homogeneous version. Now I'm telling you that it has known solutions. See, the problem with this differential equation, it does not have constant coefficients. So we actually don't have a method yet for finding the solution to this guy. But I am telling you that if you take 2t squared and you take the derivatives and you plug it in, you will get a true statement. 2t squared is a solution. Also, x is equal to 1/2 t squared is also a solution. Can I use those two solutions to form my general solution? I can't. Why not? Not linearly independent. Once again, we can see that because they're multiples, but in general, this is what we're going to do. We're going to let w, little w, equal the Wronskian. This is the Wronskian. And what is the Wronskian? It is the determinant of a special matrix. A matrix whose components are the solutions that we have, that we're checking, and also their derivatives. And basically, I have to take enough derivatives to make this thing a square matrix, because I can only calculate the determinant of a square matrix. And when you calculate the determinant, what am I going to get as a result? Am I going to get another matrix? What do I get when I calculate this determinant? A number. I get a number value, right? Or some sort of scalar function that would represent a number value given some t value. And the whole idea here, right? Well, the whole idea is that the set of solutions now, x1 and x2, are linearly independent if and only if our Wronskian is not equal to 0. So we got a bunch of solutions. I'm going to check formally, are these guys independent or not independent? I just calculate this Wronskian thing. If it is identically equal to 0, not independent. They're linearly dependent. If I get something that's not identically equal to 0, woohoo! Independent solutions, go ahead and form your general solution. Okay? So now the application is this. Let's calculate my Wronskian for this problem. My x1 is 2t squared. My x2 is 1/2 t squared. I can calculate the derivative of x1. I calculate the derivative of x2. And then I calculate my determinant. And remember from linear algebra, the determinant of a 2 by 2 is this product, which would be 2t cubed, minus this product, which would be 4 times 1/2, which is 2 times t cubed. And sure enough, I get 0, identically 0. And so that tells me that these are linearly dependent, not independent. Which we expected. Questions about the process, though? If you had 3 solutions, it would be W would be x1, x2, x3, x1 prime, x1 double prime, x2 prime, x2 double prime, x3 prime, x3 double prime. And it'd be a 3 by 3 determinant, which is a little harder to calculate, a little bit annoying. But that's the process and it generalizes. All right. Same differential equation, so you don't have to write this all from scratch. But now I'm telling you there are other known solutions. The first solution is 1. 1 is a solution. Is it really? Well, the derivative is 0. Second derivative is 0. 0 equals 0. Yes. The number 1 is also a solution. So that's one solution. Here's x2. Are they linearly independent? I know we can look at them and say they're not multiples, so we kind of know that. But go ahead and calculate that Wronskian. Calculate that Wronskian to show that they are not that they are linearly independent. All right, there's my formal statement. What do? We check for independence. We calculate the Wronskian. The Wronskian was t. Right? Is t equal to 0? Well, sure. When t is 0, it's equal to 0. That's not what I'm checking for. Whenever I tell you this Wronskian, it's not always equal to 0. That is values are independent. It shows that they are independent. Now that I have 2 linearly independent solutions, I can just put them together as a linear combination to form my general solution here. Any questions? The 1/2 did disappear. Where did it go? Into the constant, right? I can certainly write C2 1/2 t squared. I'm just lazy. 1/2 is kind of a lot to write. So. Other questions? All right. Next piece of theory. Once again, same starting right here. So you don't have to keep recopying if you don't want to here. Given an nth order linear homogeneous differential equation like that guy. Now we know that if we have linearly independent solutions, we can form our general solution like this. There is the general solution. That represents the family of solutions. Infinitely many members in that family of solutions. But I need one solution. I need one solution that fits my specific problem here. How do I find a specific solution? I need n conditions. N conditions at t sub 0 to figure out my constants. What do my conditions look like? They look like x of that initial time, x prime of that initial time, x double prime of that initial time. I know everything there is to know about this guy right now. And if I put in all those conditions, I can find a solution so that I can figure out what x looks like at later time values. Any questions so far? Just says we have a bunch of initial conditions. And we need a whole bunch of them. Now we need n of them to find the n constants of our nth order differential equation. There we go, that's part A. Same differential equation, and now we know what the general solution looks like, right? We figured out C1 plus C2 times t squared is a valid general solution. And now I'm going to give you some conditions. Find the specific solution out of that family that satisfies x1, x of 1 equals 2, and x prime of 1 equals 4. What do we do? Well, if x equals this guy, and x is 2 when t is 1, then I can apply this condition to get 2 is equal to c1 plus c2 times 1 squared. My problem is now I have two constants in here. I need another equation. Well, that's where my second condition comes from. But my second condition is a condition on x prime. It tells me what the derivative is at time equals 1. Well, if I know what x is, though, I know that x prime is just the derivative of this guy. Derivative of a constant is 0. The derivative of the second piece is 2c2 times t. So I've taken the derivative of my solution to get an expression for x prime. And now I use my second condition on that. X prime is equal to 4 when t is 1. Yep. It is, right? If it gets swallowed by the constant, it could, but then you'd have C3. And you'd be introducing a new parameter. Then I have C1, C2, and C3, and I wouldn't need another equation to solve for all three of those. So I actually want to keep my constants the same here. Okay, good question. Other questions? All right. So now what? So now I can just solve this. And sometimes it'll be easy to solve, sometimes it'll be a little harder to solve, right? You have two equations, you have two unknowns, you should be able to solve it. In this case, I'll start with that second equation. That tells me that C2 must be equal to 2. If I plug that into the first equation, I get 2 is equal to C1 plus 2, which tells me that C1 is equal to 0. And so my specific solution must be 2t squared. That is the specific member of the family that also satisfies those initial conditions. Any questions there? All right, you guys can try it for B. This is supposed to be x prime. You get some answer, check your neighbor, see if everything makes sense. What do you get here, right? You plug in the first one, I get 1 is equal to C1 plus 0. I plug in the next condition of my derivative, I get 2 is equal to 0. What's going on? What's the problem here? Set? Right. We're trying to figure this out when t equals 0. That's my t sub naught here, right? But look at my differential equation. If I apply my existence and uniqueness, it says that leading coefficient can't be 0. So there does not exist a unique solution when t equals 0. So it makes sense that when I try to put in conditions that involve t equals 0, it doesn't work. Okay? So if we know our theory, we know our existence uniqueness theorem, I look at that part B and say that doesn't even make any sense. There does not exist a unique solution there. Okay? There is no member of the family that satisfies that condition. And we can kind of see that bear out when we try to solve for the constants. Any questions there? All right. All this stuff so far has been general theory to nth order linear differential equations. Woohoo! Right, but to do anything here, I had to tell you what x1 and x2, right? To give you that general solution, essentially, right? It's hard to solve these things in general, which is why we've been focusing on linear homogeneous differential equations with constant coefficients, right? But this is just a small subset of this larger group. So all the theory should apply, and it does apply. Let's think about our existence and uniqueness theory. Applying that to this differential equation. Where does that exist in each solution? Everywhere, right? When are the coefficients continuous? Well, they're all constant, so they're always continuous, right? So that's no problem at all. That goes away. The only thing we have to be concerned about is if we did have a non-homogeneous problem and there was a function on the right-hand side, we would have to make sure that that guy was continuous. But otherwise, this thing is basically always continuous. All right, so there always exists a solution, which is wonderful, right? One of the advantages of dealing with just the constant coefficient case. You know, what else do we have to worry about? Finding linearly independent solutions. But because we're dealing with constant coefficients, we have a solution process, and it will generate solutions. And we can show those solutions are always linearly independent, right? So we don't have to check with that Wronskian anymore in this case, because we know that we will always be generating linearly independent solutions. Okay? So we have the big theory for the broad class, but then when we work with our specific subgroup, it gets much easier. All right, let's look at this guy. See if you can go all the way through this one, find the full solution. All right, step one. Assume x equals e to the rt as a solution. Step 2, generate our auxiliary equation. R squared plus 3r plus 2 equals 0. Step 3, find the roots. Well, this guy factors into r plus 2, r plus 1, which means I have roots r equals -2 and -1. Step 4, form the solution based on the form of the roots. I have distinct roots, so my solution is just some constant e to the -2t, some constant e to the -1t. That's my form for the distinct case. Remember that if my roots were repeated, my solution would look like some constant e to the rt plus some constant t e to the rt, some constant t squared e to the rt, plus so on and so forth, for however many times it was repeated. Remember, my complex case, my solution was e to the alpha t, c1 cosine of beta t, plus c2 sine of beta t. Yep. It's this thing times e to the, so no. Yep. No, it does not. So if you put c1 e to the t, negative t, plus c2 e to the -2t, totally fine. And that complex case is for roots that look like alpha plus or minus beta I. All right, any last questions before the quiz? Yep. Sure. All right, new differential equation. New differential equation, x to the fourth plus x, not x to the fourth, x, the fourth derivative of x, plus the third derivative of x. So this would be the same thing as x1, 2, 3, or x1, 2, 3, 4, right? We need to generate our auxiliary equation from this thing, right? So in this case, I would have r to the fourth plus r cubed equals 0. That's my auxiliary equation. And once again, I have to find the roots here. If it's higher than a second degree polynomial, there's probably going to be some trick because otherwise the roots are hard to find. In this case, the trick is I can actually factor out r cubed. If I factor out r cubed, I'm left with r plus 1. So what are my roots? My roots are 0, 0, and 0, right? Because r cubed is r times r times r. And my last root comes from this guy, and that would be r equals negative 1. And then I just combine all my forms. If I have a root repeated twice, my solution looks like some constant e to the 0t, right, which is just some constant, plus some constant times t, e to the 0 times t, plus some constant times t squared, e to the 0 times t. So this is the what I get from those repeated roots. And I have one more term, c4 e to the negative t from that last root. Okay, so I'm just combining my different forms for a higher order problem. Okay. Any last questions? All right, clear off the desk, put everything away, no calculator.